Heartily welcome everyone to this session. Johannes, whose profound knowledge of the JVM, will present how to extend the JVM with C++ code and speaks about the process of bringing things to a JEP, a Java extension protocol, something like that.
Fine
Whatever.
Enough.
A heartily welcome, Johannes.
Hi, I know it's a rather big switch from me presenting about bagels in a bagel shirt, but while I usually do bagels at these events apparently, like last year and this year, I also need sometimes to work, and I'll be talking about something that I worked on for like 4 years, and it's the new CPU time profiler. So when you don't see me bageling, I'm profiling. But first, what is profiling? I'll be covering now what Java profiling is, and it's quite simple. It's finding out where problems lies. But let me take you on a journey. Because it's also, you might know the Night of Sciences, the Nacht der Wissenschaft, which is a community event by students where you can give presentations like here at the Gulag Programmiernacht with less fun and more professors. But essentially, during Corona, we had quite some fun. We also wanted to have an event, but we had one with streams, but we wanted to have something with interaction. So what we did was we developed an application, in this case me, because I was doing a PhD in the time in computer science, where you could answer questions like how old is X, how old is the universe, answer it, and if you win, you get a prize. It was quite nice. I was like, that's why I studied computer science for 6 years at KIT. Can do this. I thought I'm lazy. I just have a client that regularly polls the server and is like, hey, do you have a question? If yes, give me the question. And then we have a single admin interface. The interesting thing here is that I was like, I don't have so many clients. I just store all the data in a JSON file and let the file system do the synchronization. That's probably fine. Because with Donald Knuth, premature optimization is the root of all evil. You probably all heard this quote. Who has heard this quote before? Yay. Yeah. The fun thing is, the event came, guess what happened? What?
A lot of clients.
Yeah, client number wasn't a problem. Well, of course it was overwhelmed, yes. I don't think that it's the clients, it was just there was no testing. Anyway, who needs testing? Because we usually use the shorter quote. The longer quote is, we should forget about small efficiency, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up our opportunities in a critical 3%. A good programmer will not be lulled into complacency by such reasoning. He will be wise to look carefully at the critical code, but only after that code has been identified. So how do we identify it? We use profilers, yay! If I talk to my one non-computer science friend about what I do, and I'm like, I do profilers, they're like, are you someone like CSI or Sherlock Holmes? And looking for who killed someone? I'm like, probably not, because I know who it was. It's give blame, thank you. But I want to know how it happened, and so it's still quite similar. In this case, we're using on the top the pseudocode here, and on below you see a flame graph building up. A flame graph is a simple tool that essentially throws the time information away and just looks on the duration. So for example, main spent the whole time there. So it's the biggest bar. Then the server loop, which is called, spends most of the time in there too. Then, of course, in server loop, we have different kinds of requests, for example, admin requests, but we don't have that many admins, so it's fine. Essentially, we have one. And then it checks, is this a question request? And if so, handle a question request. Then what does this do? It emits the current, it checks, is there a question enabled, and then emits the current question. Any guesses what both methods spend most of the time in? in parsing JSON. Yay. That wasn't nice. Like it was literally, but it was looking this way, so it wasn't idling. It was literally just spending all of its time parsing JSON. It was an efficient way to heat my room. So you saw the flame graph directly what went wrong. To quote Mario Fusco, I love flame graphs when you do something stupid, it punches you in your face and it's impossible not to see it. You saw it before, like, yeah, I did something wrong. Probably wrong decision. Then, of course, the sensible thing, use something like SQLite. I don't need something overkill. I don't need a whole Postgres database for just a few users. Yeah, the only problem was Corona is over. We can meet in person, like here at Gulasch Programmiernacht. What a pity. Couldn't use it, but it's a good talk. It's a good topic for a talk. So, hey, good things come out of Corona being not there anymore. Anyway. No, I think profiling belongs to a toolbox like debugging, like testing. Learn what profiling is before you need it. So what is profiling? I think you probably all know the jargon file. The jargon file describes a profile as a report of the amounts of time spent in each routine of a program used to find and tune away the hotspots in it. That's quite nice. We probably need some profiles, and there are different profiles. For example, in Java, there are ones that are external, that you bolt onto, and there are ones that are built in. It's essentially like with a bike, where you can have a speedometer either built in, because, for example, it's an e-bike, or you have one that you bolt onto your bike that still knows a lot of information about your bike, for example, speed, but isn't like tightly coupled. And with the external ones, they're essentially old ones like Visual VM. Then there's Async Profiler that came out of Thought Analyzer. So in 1991, Sun wanted to have a profiler for the applications. They developed Thought Analyzer. Then in 2002, they wanted to support Java. Yeah, they added a call. They added a method called async@callJS that we see in a bit. And then 3 months later, removed it from the official exports, but you can still use DLSim to access it. Anyway, that's used now for all major profiles. Till the last few months, it's changing because there are problems, as you see in a bit. But then there's the built-in ones. The main one is, or the one is the JDK Flight Recorder, open source in 2018. And we have here the Wall Cloud Profiler. Empty space, I know, besides it. A coincidence. Anyway, the cool thing with JFR is it's simple to use. Like, know probably how to call Java. Just pass it like, hey, please start it. Thank you. Here's the file name, and then do something that makes it more precise. These flags don't change that much. They just make it more precise. They don't have performance penalties. It works on all platforms. Nice. Even on Windows. I might have heard for some other sessions that Windows is pretty nice to use, especially to administrate. It has so many events that I thought I'll build a website where you can just look them up, because it supports like 126 events, so you can see object allocations sampled, or you can even see information on all the compiler inlining, which is information that you probably won't ever need, but I think I have colleagues who like to have it. It even has custom events. It was quite funny. I was looking into these and then found out that Minecraft, which is written in Java, has events. So you can type /JFR and get custom JFI events for Minecraft. So I had a problem. I want to write a blog post about it, so I need to play Minecraft. The problem was only computer that it ran on probably was, or that the computer that I installed it on was on a big tower PC, like these Lenovo ThinkStations. They have a built-in speaker that plays Minecraft music. The only problem is it's a tiny, tiny, tiny speaker, and I can tell you the music doesn't get better if it's piped through it. Like these, I don't know where they find these speakers anymore. Anyway, it was quite fun. JFR can be used everywhere. Anyway, but it's not perfect, as you see in a bit. because how it works, simply the profiling is every n milliseconds, for example, every 20 milliseconds, it captures 5 stack traces. So it picks the next Java thread that's not blocked, suspends it, so stops it, using using usually Unix signals or stuff, then captures the stack trace, walks it, then resumes the thread. The next stack trace still has 5, that's fine. The QR code links to a FOSDEM presentation that you can watch where I presented this with a friend there or with a colleague from a different company. If you want to learn more about this. And of course, this changed with 27, but you've seen a bit foreshadowing. Not my work. The only problem here is that you see here there's a sliding window, and also has problems when you have an error rate, because then you sample 5 stack traces, you only get 4 back because 1 errored. You don't notice that you errored, so it's not really good. And also a problem is when you consider here, down the x-axis you have the number of threads currently running in your system, and the y-axis is the effective sampling period in raw clock time. Problem is it scales linearly. That's not nice. You can't say, oh, I have 10 samples, so so the method ran a certain amount of time. And there's no clear relation between CPU time and samples because it's like kind of raw clock based. So how did I end up giving this talk here? The fun thing is I gave this at another presentation, so you have to follow through the rest, and then I tell you that I just did baked bagel, and then I happen to stand here. But anyway, so I got onto a train, onto a bus. I traveled a lot to conferences, baked some bagels apparently. Hi, I hope you liked them. And gave a talk on this, and then I ended up being, now, how did I get really involved? Well, I'm Johannes Bechberger, as my herald gladly said. I work at a team at SAP, you might know them, a big company in Waldorf. We're one of the many big open source projects here. With Submachine, we're like the 3rd biggest contributor to OpenJDK. So my colleagues are literally developing Java. They are not Java users. And we, for example, do the PowerPC port of Java and started the S390 port. It's still going strong. Or the AIX port that we're currently doing. Yes, people are still using these platforms, and you can run modern Java on them, which is cool. The colleagues are fine. One of them even did the CPU development at IBM. Anyway, that was my first job fresh out of uni. So I studied here at KT and then tried to do as a PhD with processor smelting. Some of you might know. And I was naive. I was like, yeah. So my problem there was the first assignment that I got when I started was, hey, help this colleague implement a feature in a profiler. And I'm like, sure. I'm happy to do this. It was fun, and I was like, couldn't we get a better API? Yeah, and that's how it started. 4 years later, I'm still alive. It scars you. No, on a serious note, I just was naive. A colleague at the time told me, like, from a different country, you're digging yourself a well. It's deep, high. So this talk can be actually titled as One Man's Journey to Improve Java Profilers. And so in the following I'll be showing you how you can go from there, having a profile, to a profiler where essentially the kind of sampling rate built down below is linear, so you can have much more meaning out of it. What you'll now be seeing in most of the talk, in most slides, is that you see the time code down below, so you see where we're standing. The fun thing is, I'm just using old presentations here. I'm trapping together the presentations that I did at the time with some clue slides. So if you've been in the last years at my talks, there are GPN talks in there, which is funny because many people I usually gave this at bigger conferences, like at normal IT conferences, and they see slides that nobody except you have seen before, and that's quite fun, where I'm like, oh, I don't tell them that I give the fun talks at these events like here, like my bagel talk before. Anyway, we started in 2022, quit my PhD, started doing an OpenJDK, so I'm a full-time open source developer, and I had to look into async profile and a common profile, so how does it work? Better than PowerPoint. So essentially what it does is that in the most simplest way, you have all the available threads, it samples a few of them, and then you signal a thread and say, please stop. And then you walk the stack in the signal handler in a pre-allocated way. That's all. Of course, it has also CPU time profiler, which uses Unix signals, but essentially it works the same. You get signals to a thread, then in the thread you do something in the signal handler, and it's cool while the thread is stopped. And then you store it somewhere. And then, for example, generate a flag graph. How this async get call trace works is pretty simple. So you have this stack here. The green part is the Java part, the red part is the JVM. So down below, on the bottom, which is fun because most stacks are pointed the other way around, so don't be confused. Or like showing the stack is always confusing. But anyway, down below you have like the preferred start, and up you have write implementation that's in native. So what it does is async get call trace gets past the U context, every signal handler gets past this. And then you get the frames, and then you also pass it the frames where it stores the data in, and the number of frames it collected. And you get some information. You get the line number field there per field, which is actually the bytecode index. Don't know why it is this way, but it's this way since a long time. And then you get a method ID. The only problem is that it's unofficial, it's unsupported, it missed tests. There was one that I fixed then because it was not testing anything. It missed information. That wasn't good. But it's the best that we have till hopefully soon. Till we wait for JVM-TI replacement. So how I started was I thought I could do this better. How hard is API design and convincing 100 people to adopt it? Couldn't be that, couldn't it? That's my first JEP, by the way. I wrote 2. This is JEP 435. You can read it there. It's the asynchronous stack trace VM API. You see, when I started writing this, it was created in April 2022, and then closed because nobody wanted it. It defines an efficient and reliable API to collect stack traces asynchronously. Essentially what it does is you parse it. It works like async get call trace. The only difference is that you also get the kind. So you can also, for example, sample native stacks. And also you get far more information. You get the bytecode index, cool. You get a method ID to reference the method. But you can also get the types like inline and also the compilation level. It would just help a lot. We wouldn't then have a lot of options and even have C++ frames, and it would be fun. I thought about it, I implemented everything fine. While I was working on this, I was like, yeah, it takes time, it takes round-trip time to contribute. I developed my own profile frontend that is updated as of now to a new version that's far more efficient. So, yeah, you can try it out. The QR code is at the end of the slides. It's essentially the first and only open source profile plugin for IntelliJ that fully integrates with IntelliJ itself. So you can just profile and view all the JFR data in there. Then in 2023, I was also here at this very event, and I gave my talk called Nightmares of a Profiling Developers. Nightmares of a Profile Developer, Johannes Bechberger's gruesome tales on Java profiling APIs. It was quite fun. I gave it a night, and I lit my face from below. It spoke like this, because I was slightly annoyed by these APIs. One of the issues was here when I was working on this new version was method IDs. Well, you all probably know that Java is class unloading, so classes don't exist always. So what happens then is, let's see, is that I always want to use this in a presentation. Yeah, it's not good. It can explode. It can literally kill your JVM. That wasn't a good thing, and it didn't happen with JFR because they literally just had a wrapper before you called the stuff, which is the crash protection wrapper that just like when it crashed, it was like, it's fine. That's how you develop software. No, it was good at the time, but still, like, it's unsatisfying, isn't it? The problem here with this is save points. So, what a save point, or one of the solutions here is save points. Save point is quite simple. So, every time in your program, multiple times, the JVM asks, hey, should I maybe execute some other code? So, for example, should I execute a garbage collection or stuff? And that's called a save point. Points in where the thread itself asks, should I stop? I'm in a defined state, I'm fine, should I stop now? This is usually at the beginning of methods and at the end of methods. It's also at the loop back edges, so every time you jump back in the loop, it's also in there. And that's pretty cool because this allows us to do things like garbage collection where the thread needs to be stopped and needs to not be in some kind of copying operation or something that you don't want to interrupt. The fun thing here is any idea how this could be implemented? That hints maybe on it, but any idea here how you could implement something where the best case is pretty efficient. It's low in bytecode size, and it's and the worst case you don't care about. It doesn't happen like 100 times a second or something. Any ideas?
Basically, you use a page from the operating system, and the running thread basically just tries to read a random value, and the JVM can protect it at basically randomly, and then you can't read from it anymore, so the JVM will cause a seg fault.
So I'm saying this again for the stream. I think you were in my talk before, and you remembered. Okay, and yeah, maybe it was too easy as a question. I'll note this for later. Anyway, so the idea is essentially a JVM seg fault on purpose, because producing a seg fault is quite easy. You just move on a write protected page. Gut. Oh, schön. We have microphone angles. Tolle. Sorry. And that's pretty cool. So in the best case, when we write a restricted page, like it's fine. When you have a good page, nothing happens. That's fast. It's also less bytecode because every bytecode you introduce, or every assembly with every assembly instruction you introduce adds more problems for code cache and something. And in the bad case, you just seg fault because that's the bad case. You didn't query the seg fault handling takes some time. And then you are in a safe point, and that's pretty cool. The only problem is with debuggers. They don't like it. They think your application is broken when you seg fault. But this thing seg faults 100 times a second. GDB really hates it. Anyway, now the question would be like, why not sample at these safe points? Like at these points, it's safe. You don't crash your JVM. Like you know that the JVM is in a state where it's usable. Yeah, concern now this is the mascot of my team, of the submachine. We like puns here. And every time it's like dark or darker, it's in there or saturated. It's in its I check the save form mode. The problem is now with the save form points, it's like saying to it like, stop, please, when you're ready. You saw that the program like did some work in between. What we need with fully asynchronous, and we want to say, stop, please stop. And that's cool. The problem is with safe-point bias profiles, to quote Nitzan Wackert, who is a passionate profile developer, developed many of the tricks we currently use. Safe-point bias profiles are tricksy, snicksy, filthy, all of the above. He also called them, for whatever reasons, lying hobbitses in his talk. Don't know what it means, but I think he doesn't like it. So what do you want? The German I would say, no. What I really want is unbiased safe-point-based stack walking. Doesn't this sound like an eierlegende Wollmilchsau? Yes, it does, but it's doable. I even wrote a blog post about it. No, the idea, it was quite fun when this was like in 2023 when I was traveling to Milano and did a user group there, and I was sitting on the sides of the train station in Milano, and then I had a call with Markus Gröndon, and he told me like, hey, there could be this way. I'm like, okay, I tried it out and it worked, but he did it better, so I'm happy that he did much of the work. But anyway, there's some ideas here. Because the main problem is we still, what we want to do is we want to walk the Java stack, because this might change or be interrupted. We want to walk the Java stack at the full Java stack at save points. The native stack we don't care. And then at the save points resolve the methods, because when we at the save point do all our resolving stuff, the method can't be the method can't be like unloaded, because like we're literally at the end of the method. So what we do is quite simple. We walk the stack trace in the signal handler until we hit the first Java frame, like the first non-inline Java frames. We don't care about inline Java frames. We don't see at this point. We don't resolve these. We don't know what is an inline Java frame. We just see the first full frame that we can associate with something that lives in the Java in the Java code area in our heap area or in our code area. And so what we do then, we push the information into a queue. So we say, we save the program counter, stack pointer, and the function pointer. And an interesting thing is, now with the save points, we can walk this queue and then reconstruct the first top frame. And then also from this, because we're at every end of a method, we have a save point, we can then walk back. So that's pretty cool. This means we can have unbiased save point based stack walking kind of, and yeah, that's just nice. I have to say here that the save point is like at the end of the non-inline method. Yeah, I had many more ideas for this. I thought I'd make the best profiling API ever. Like, that's what you do when you are naive. The only problem is that JEP faced some oppositions, including some Twitter discussions that got heated. It's nice to be inside a tiny Twitter flame war. I can really tell you it helps you a lot. Anyway, then 2024 came. And I spoke at a few conferences. Hi, for example, here again. Thanks for having me, of course, also in 2024, gave some talks, and I had a fateful chat with Ron Pressler. Ron Pressler is someone who works closely with people who want to do JEPs and who's working at Oracle in various positions in the Java team. And I spoke with him after FOSDEM at a JK committers workshop, and he essentially told me like, hey, what do you really want? Like, you don't want you can't improve async call trace like you would do, because most people don't like async call trace. They want to rip it out eventually, if they could, but it's used. So, so what do you want? And I'm like, yeah, a CPU time profiler would be nice. That's what we want, for something that we can easily use and it doesn't go away. So the idea here is, with this, every 10 milliseconds on time on the CPU, we get one sample. That's pretty cool. So ignoring, this way we ignore also any weight, so we focus on the computation. So I showed you the slide before. It's flat here, so even if the number of threads gets higher, gets far higher than your CPU count, the effective sampling period related to CPU time is always the same. That makes it far easier to reason about what hitting 10 samples or with a method being in 20 samples really means. And that's pretty cool. So now we have a new CPU time profile here. It's pretty cool. Let's look at an example. I now start a server, and this is from the JEP, from the JEP enhanceable proposal. We have a server that has a fast request that returns in 100 milliseconds, and then you have a server that returns after 1 second with a slow request. Now we have a client. The client makes 10 fast requests, and then it makes 1 slow request. What we normally would expect that, of course, 10 fast requests are usually a bit slower than 1 slow request, or that we get more samples in there. But with the default profiler, what we get is the same, because relate to wall clock, it's the same. But that's usually not that helpful, especially in this case where we're really looking at computation. So with the CPU time profiler, 1 slow request disappears. It's just the heuristics. The actual flame graph looks like this. Yeah, it's disappeared. Yeah, it's a heuristic. You sometimes don't hit them if they're too short, but we would expect something like this with a higher sampling rate. And it's pretty cool, and it's helpful for finding computational bottlenecks. But implementing it in JEP, as a JEP was hard. Yay. Who could have guessed? Yay. Now, then in 2025, it was interesting because it was cool that Markus Grönlund implemented his ideas into the normal workload profile. So he changed it so that JFR got cooperative sampling, which means that you also in JFR only sample at save points the whole stack, which is so much nicer because you don't have to have the thread crash protection. So JVM crashes less and then has to catch itself, which helps a bit. And it's the JEP 518. The cool thing, it got merged before JK25. So the problem with Java is that we have LTS versions, which kind of means that the LTS versions are supported longer by a provider. For example, we at Submachine, we support like JK21 and 25 far longer than we would any of the minor versions. So that means that normally people won't use any of the JDK 22, 23, 24 at all. That means when I get a feature into 26, it could also be in 29 and I wouldn't see a difference in usage, which is a bit of sad. So it was really good that it got in there, and otherwise I would have to wait 2 more years to get it in. So I was happy that this got in, and this is my JEP here. It's marked as experimental because the event is experimental. It's the JFR CPU time profiling one. It says here, enhance JK flight recorder to capture more accurate CPU time profiling on Linux. This is an experimental feature. It's still there in 26 and 27, so yay. The basic idea is pretty simple. So we register an iTimer. This is a way where you can, on Linux, say every 10 milliseconds of CPU time per thread. You do something in here, you capture the tip of the stack trace, as we've seen before, push it into a thread local queue that must be bounded size, because in signal handler you can't do really memory allocation. And this is also the reason, by the way, why you have a samples lost event, why you can lose samples, because like the queue is full. Yes, we do some clever resizing, that's fun, but still the queues might fill up. And then at save points, we reconstruct all stack traces and create the events by walking the queue. Now the question, do we only walk at save points? We only walk the stack at save points. Any ideas here? Like we saw before, we want to do this, but are there cases where we also want to walk even when we are not at the save point? Does someone has an idea when it could be that the time between 2 save points is pretty darn long? Yes. That's a problem, because we do this in Java quite a lot, like, let's say database calls, say some network operation. And essentially what you have at the beginning of a native method, you have the save point. So we check for a save point, and then in the end we have one. So what we do is essentially, whenever we are in native code, we tell our other thread that's like walking the queues asynchronously to the threads. We tell like, hey, please, for this thread, walk the queue. What we then do at the end of the save point, we don't want to have this thread walking the queue concurrently and the stacks to our thread currently like running here. That would be a problem. But what we can do at the end, at the save point that's before our Java application or before our Java code then starts again, we just wait till it finished walking. That's nice. That means we lose less samples. The implementation is slightly more difficult. That's the actual diagram of the code that I created. Yes. It's not as difficult when you consider it's like 2,000 lines of code and it worked a couple of years to get this in. The actual code implementation wasn't that hard. It was probably like, but then you test and you find another bug. It's a fun thing when you're like at home sitting there and in front of your computer and you're like, yay, another sec fault. Or yeah, it was quite fun. So it got in time, as Markus Grönlund here stated on the pull request. Essentially he wrote, we have reached a state that is good enough. So there's no longer any fundamental design problems. And hey, it should be still possible to get it into 25. That would be cool. Fun thing is, it got so short on time in that I need to press a Jira button, whatever. But I did notice I was walking with a friend in the evening, like I live not that far in Karlsruhe away, so I walked like to direction of the ZKM, and then shortly before the ZKM I got texted by multiple people on Slack like, could you look into Jira and press this button, please? And I did, ran back home. And then it got in just barely. So quickly that Nikolai Parlok, a Karlsruhe-based DevRel of Oracle, was saying like, thanks for pushing it through last minute and making me work late, because he had to record parts of his "This is new in JDK 25" video. The only problem is I got the comment that you don't want to hear after you pushed it in the morning. Hope you haven't gone to sleep yet. There it falls on links. And it was a 3 at night, and I went to sleep. It wasn't Gulasch Programmiernacht, so yeah. And he proposed a fix. The fix didn't work. I fixed the fix. And then it got in at 7 in the morning. It was good because the person like saying final cutoff and something, he's in the US. So that's not bad. So we still had some time, but it was like, shit. Anyway, this was fun. But of course, I wasn't alone. I was working with other colleagues like Jaroslav Bachweg or Andrei Pangin or of course Ron Pessler. So working on the OpenJDK is great. We work together on projects, but it's also work and it's a lot of compromises. It's just hard. It's many companies working together, many people working together with different compromises. Now in the last few minutes, I tell you how to use this thing I developed. So what you do here, you enable it by saying jdk.cpu time sample enable to true. It's not enabled by default because it's experimental and it works. And you can configure it in two ways. You can either say by a throttle parameter like what the CPU time interval is, but this is a problem when we want to have a general setting that works on all cores, because on all core counts, because when we say like 10 milliseconds and you have a 100 core system, then you get quite a lot of events. And you get like 10,000 events a second. That's quite a lot. So we can compute an upper bound because we know the maximum, we know the cores. we can also adapt this dynamically. That's pretty nice. We see, of course, some information, the information that we found before. We get a stack trace, and when it happened, and also on which thread the sample happened, and then we see whether it failed. So, like, we don't hide it when we fail with stack walking. So you still know that this thread was on the CPU at the time. We also get a sampling period from the operating system, because Linux is so kind to give it to us. So how long was it between this and the previous time that the signal handler kicked in? And of course, where there's bias, because sometimes we need to walk at a safe point, kind of because we can't reconstruct the frame. And of course, we get in also the samples lost. Yeah. Problem is, of course, it's experimental. It might go away, and I still need to optimize some of the memory ordering, but memory ordering is hard. I heard they tried it and it failed. I wrote a blog post and I saw, oh no, it worked, and then rejected the blog post, whatever. Development is hard. The thing is, I work in the open, because I'm working on open source, so you can see everything that I tried and that fell and that didn't work. Or even go to the Gulasch Programmiernacht website or here in the video repository and see all the ideas that I had in full. So the other problem is it's only available on Linux, because I'll buy systems like macOS, probably also FreeBSD or something, have the ability to give you an I timer related to CPU time. This is always just related to the CPU time of the whole process. That's not great. So this is currently sadly only available on Linux, which is a pity, because I can't do live demos, because this is not a Linux. It would be fun. It would be cool if I would have a proper Linux on it, but that's how it goes. Anyway, it was really nice doing this whole work. It was a journey of 4 years, and I ended up here again. So if you want to find out more about JFR and stuff, I wrote a blog post semi-regularly now. We also shared a new waffle recipe for whatever reason. That happens when you stay at the blog too long. You find me on GitHub. You find my team at submachine.io. And above is the link to the Java profile plugin for IntelliJ. It is now updated. Thanks for being here, and have a nice time. Have some fun rest of the day, and see you.
Thanks a lot, Johannes, for the insight into the intrinsics of the JVM. I myself only am at the top level, in the user level normally. So very interesting talk to see how it's even hard to get something new into the Java JDK because of the JEPs. It's very enterprisey. Anyone? Are there questions? Ada, wasn't it?
Does this add any save point overhead at all?
You mean, is the save point any overhead, or is it a problem that they do something in save points?
When you hit a save point, does it make that save point longer?
You mean with my CPU time profile?
Yeah.
A tiny bit, but capturing the top Java frame, if you aren't too deep in like the native, of course, if you have like 1 million native frames on top, but usually it's pretty shallow and I know, a couple of hundred memory accesses, and I think the whole process of doing like coming into a save point and then like handling, oh, this is not a proper seg fault, but a seg fault because of that, could be probably much longer. So it's not really a problem that you do this.
Okay.
And if I'm honest, like signal handling in and of itself also takes time. So I think walking the stack for like 100 or something frames is not really that big of an issue.
So I must admit I have not done Java in a while, so maybe that's totally off. But for other languages, I usually use the Linux perf tool to generate like stack traces and stuff like that. Is that not possible with Java because it would be hard to symbolize that stack inside the JVM, or how does it work? So it's more like a question, like a meta question.
That's an interesting question. So you might know that for perf you have perf maps, where essentially a program can say, oh, by the way, resolve this frame as this method, or resolve this function pointer as this method. This also works. I think it even was Nitzan Vakart, if I'm correct. Maybe it was someone different who created for Java 8 such an agent where you could use perf with this. In your version, it's apparently not that easy because nobody did it. It's far harder. There are people who are doing this for eBPF, so they export this information, and so it's kind of perf-based because I talk with people who are using in eBPF the perf event that you can also hook into. So it's kind of used nowadays by some of the more modern tools. So yeah, kind of. But no, simple perf doesn't work because you only see the native frames, and perf doesn't know what Java does, like with all the just-in-time compilation.
Are there further questions from public? 3, 2, 1, 0. Thanks a lot again, Johannes, and another big applause, please.